Hello Internet, my name is Quinn and this is Blondihacks. We're back on the steady rest project today. We're going to make these little fingers that do the steadying and the rest. They were a lot of fun to make, so let's go. Quick recap of what we're building. Shown here in pink is the original casting for the steady rest that came with my lathe, or 1/3 of it, and all of that other stuff is what we're building. In the previous video we built a bunch of the minor parts and we also remachined this casting. And now we're going to make the actual fingers or legs of the steady rest, shown there in yellow. It's a pretty complex part, but it should be a lot of fun to make. I'm going to make this out of some 1018 mild steel square bar, which I didn't have on hand, so I went to my go-to source for this sort of thing, eBay. So I found a couple of pieces here that should do the job. Now I noticed right off the bat that this stuff smelled different than my normal 1018 steel, and that'll become interesting later. But for now, I set it up in the vise, and I decided to square up the stock and get it to dimension for all 3 fingers in one go. So I've got a 9-inch chunk of it here, and I'm going to machine the whole thing down all at once and then cut it into pieces. So my go-to for this sort of thing is this big 4-flute 2-inch shell mill. So I started off by doing a light facing cut, get my speeds and feeds dialed in, and this seemed to be going well. There was a little bit more smoke than usual, and after a couple of passes I noticed the chips were coming off really hot. The chips are blue and they really shouldn't be. And then I noticed that my cutter was unusually warm. And then I took a closer look, and the business end of the flutes, those corners, they're all burned up. This is only after a couple of passes of like 30 or 40 thou. I put a file on it to see if it would bite, and it does, so it's not completely hardened, whatever this is, but it's really hard stuff, and it ain't 1018 mild steel, that's for sure. It completely burned up that cutter. It's going to need to be reground. I put out the call on Instagram, and the general consensus seems to be that this is probably 4140 or 4340. It might actually be stainless. It smells like stainless to me. I'm not claiming that I can identify steels by smell, but it does smell like the other stainless that I have, so take that for what it's worth. But I had to start over with some new stock, this time from McMaster Carr, so I know what I'm getting. eBay is a good choice for cheap offcuts, but yeah, you don't always know what you're getting. The sellers may not actually know what the materials that they have in their junk boxes are. Same setup here. I'm going to be squaring the stock for all 3 fingers all at once, and I'm using machinist jacks on the end there for some extra support because I've got a lot of stick out. I'm going to use this 1-inch high-speed steel cutter that I found in the junk bin. This was donated to the channel, and it's of unknown origin, an unknown quality, and dubious sharpness, but I thought I'd give it a shot since my big shell mill got all burned up. And I'm cutting on the narrow edge first this time, so I can narrow the stock down enough to where the 1-inch cutter will do a single pass on the other face when the time comes. And it's cutting okay. The surface finish is not very good, so I suspect this cutter may not be very sharp, but we're pressing on and getting the job done here. So this setup is a little complex, so I have to deburr after each face, just like you would for any squaring up of stock, but then I also have to clean up the area around the machinist jacks and reset everything. So it's kind of one of the disadvantages to a complex setup like this one. Squaring stock is changing faces after each pass is quite a bit more work. But these chips look a lot better, so this is in fact 1018 mild steel. You can see there's a little bit of a yellow tinge to the edges of the chip, which is kind of what I like to see. I'm checking the dimension at both ends as I get close to final dimension, and I am finding a couple of thou of taper here over 9 inches, so I'm going to leave it a few thou large so that I can come back later and clean up this surface finish and also correct any taper that might be in the individual segments after I cut them apart. And speaking of final dimension, I got out the gauge blocks. These were a recent donation to the channel. Thank you very much for all the people that offered to send me these guys, and I'm just checking what my actual dimensions were that I achieved on these slots when I remachined this casting, and interestingly they all came out pretty much exactly on 749 thousandths, 1 thou under what I was aiming for. Not sure how that happened, but at least they're all the same size, so I'm gonna match the fingers to that size rather than trying to remachine this casting, because that was such a difficult thing to do the first time. I have no desire to do it again. To square up the ends of the stock, I'm using this wicked looking cutter from Niagara. It's high-speed steel, it's got some kind of coating on it, and it looks like the finger of Cthulhu, which makes me happy. And it's doing a very, very nice job of squaring up the stock here. It's just mowing through the steel, and the surface finish it left behind is just beautiful. So it's only 3/4 of an inch wide, not 1 inch like the other one I was using, but I think it'll be my go-to for future operations on this stock. And now that we got everything squared up, again, still a bit oversized here, but I'm going to cut it into the 3 pieces. And I'm going to do this with the horizontal bandsaw, which is kind of overkill for these little pieces. But the reason I'm doing this is that this saw cuts very square. I know that. So this way I only had to leave 50 or 100 thou between each part, and it'll be easy to clean up. You can see how nice that cut is. And so now I can come back in and square up the ends of each of the 3 pieces and bring them into the final dimension that I want, which is right on 3 inches. And next I want to clean up the finish if I can and remove any taper that's still left in these parts. So I'm using the shim technique to very carefully dial in my cutter and shave just 1 thou off the 2 sides of this part, so that I can bring it down to dimension. It turns out I only had 3 or 4 thousandths of room to play here, so I'm taking very, very light cuts. You can see comparing the short side, which was just machined with this new cutter, and the wider side on the front there, which was done with the old dull cutter, and you can see the difference in surface finish there. And these shorter pieces were much easier to get square and true, so these guys are now within 1/10 of the same width all the way down, which is great. That taper is gone, and they fit in those slots just beautifully, so that is great. And I decided to try some emery paper to clean up the wider faces, just to see if I could take those tool marks out without removing material. So I've got my emery paper set up, 320 grit on a piece of glass there. I'm trying to get out of the habit of using my surface plate as a lapping stone, which it's really not good for it. And you can see that does quite a nice job of improving the finish. So this is an option. It's fairly labor intensive, but in the end I decided to go back and take 1 thou off of the wide sides as well with that really nice 3/4 inch Cthulhu cutter, and that did a great job. I would say more than half of this project was actually spent making these blanks just as perfect as I can get them, because the dimensions and squareness of these blanks is really going to dictate the entire feel of this steady rest when I'm done, so it's really important to get that right and spend the time to do that. Now we can set up to put features on these blanks. So I'm setting them up using the end of the vise as a stop there. And I'm edge finding to get an origin. And because the part is symmetrical along the x-axis, I'm using the end of the part for x0. And for y0, I'm using the center line of the part with the half function on the DRO. When features are symmetrical, it's much easier to have 0 in the center, because then it's just plus and minus on that axis for all of your distances on the DRO. And so I've got an end stop set up there as well, and I'm spotting all 3 holes on the first part. And then I can easily swap out to the next piece and do the same operation on the next piece. And this will save me a lot of tool changing and setup time. So the 3 holes that I'm spotting are the hole for the pivot pin on the bearing at one end, and then the 2 ends of the slot that we're going to be cutting. I like to drill out slots before machining them, as you'll see here in a moment. So this is very quick to just use the same 3 positions on the DRO, swap out the part, swap out the next one, and continue. And then we just switch out to a drill and prepare to drill out the ends of the slots. And so the slot is going to end up being 390 thou wide. So I'm drilling this out to 3/8, 375, and that'll give me just enough room left to machine the outsides of that slot and clean up the surface finish when we're done. And then once again, I just swap out and do all 3 parts with this one operation before moving on to the next. When you have multiple parts to do like this with complex features, this is a very efficient way to get it done. And if you use an end stop like that, this setup is extremely repeatable. As long as you keep your setup clear of chips, then you won't have any trouble reproducing the features from one part to the next by doing it this way. And to cut out the slot, I'm going to use this badass carbide 3/8 cutter, another Niagara cutter that was donated to the channel. Thank you, Dennis Nolan. And we're going to put this guy to the test for our slotting operation. And here you can see why I drilled out the ends of the slot so that I can move downward to set up a depth of cut without needing to plunge with the end mill. So you can go down however deep you want, throw the power feed, you cut your way across the slot, and then at the other end, you just stop, go down a little further, crank the power feed back the other way, and your slot gets cut just like that. And by milling the slot undersize and then doing a finishing pass around the outside with a smaller mill ensures that we get a slot that's on dimension and has a nice surface finish. When slot cutting like this, one side of the end mill is conventional milling and the other side is Klein milling, and so you get a lot of very strange differential forces on the cutter, and you'll see that in the surface finish, and you'll tend to end up with a slot that's a little bit oversized. Another challenge with slot cutting like this is chip control. So when the slot is shallow, you can see I'm using a brush to keep the chips away so I don't recut them. When the slot gets too deep for that, one option is Anchor Lube, which is a thick soap-based cutting lubricant, and it works pretty well to pull the chips up out of the slot. The chips will ride up the cutter in the goo that is created. That works fairly well. It's kind of messy stuff. Another option that I like a lot is simply putting the vacuum in there, and that keeps the chips clear of the cutter and also gets air moving over the cutter to keep it a little bit cooler. So this is a great option, and the one that I ended up going with for the rest of these cuts. And this vacuum, by the way, is the Fine Turbo 1. It's this thing will destroy every preconceived notion you have about shop vacs. It is quiet, it is powerful, it's a joy to use. It's not cheap, I won't lie, but hashtag not sponsored. I'm going to link to it down in the description. This is some of the best money you'll ever spend in your shop, and this is coming from someone who loathes shop vacs. All right, now we have a round-ended slot cut in all our pieces, and you can see the surface finish is not great in there, and we also need to square up the corners. So we're going to do that with this little guy. This is an 1/8" carbide end mill. And the only disadvantage that this guy has is that the cutting area, the flutes, are not very tall. So you can see that it's not going to reach down far enough. I wouldn't want to try and do a 500thou side milling pass in one go anyway, but as we get deeper into the slot on the second pass, the shank of the tool could potentially rub. So to get around that, I'm going to pull a trick from the Stefan Gottsvinter playbook, and I'm going to neck down this end mill a little bit using the D-bit grinder that we spent some time refurbishing. This is its first real work here in my shop, so I'm very excited about it. So I just put this guy in there, and I took about 5 thou off of the area above the flutes, and still giving me plenty of room to grab this guy with the collet and leave enough for rigidity. And I marked it with nail polish just so I don't forget that that area has been necked down, and I don't try to grip it in that area with the collet where it wouldn't hold properly. And so now we can do a clockwise lap around the outside of our slot, and this simultaneously squares up the corners, leaving the 1/8" internal radius that I want according to my drawing, and also cleans up the surface finish on the slot. And this is an easy operation because we're only taking about 5 thou off, which is all that was left by the large end mill that we used to cut the slot. And here you can see the little lip halfway down where the end mill was able to reach, and then we just lower that guy down to get the bottom half, do another pass, and here you can see we're really flying the machine on instruments because you cannot see from the operator position what this end mill is doing at all. So you really have to trust the numbers on the DRO and really listen to the sound of the machine and the feel on the hand wheel so that you know when your cutter is in trouble or when it's doing well. One thing that's fun about a small carbide end mill like that is that the RPM is easy to calculate. Set your machine to balls out. You pretty much can't run an end mill like this too fast, and especially in a hobby mill like this that arguably doesn't run fast enough for this type of end mill. But I'm very happy with the end result, so now we can do the other two the same way. And then I set up with a drill that's one size under 1/4 so that we can drill and ream this hole at the end of each finger to 1/4. This is where the pins go through that hold the bearings. So this is a very straightforward operation. We already spot drilled these previously. With a nice repeatable setup like this, it's actually fun to just swap the parts out like this. It's very satisfying when they click into place, and I am tapping them in between each setup just in case that wasn't obvious. And then we go in with the 1/4" reamer and finish out this hole. This reamer is a little dull, so my surface finish in that hole isn't very good, but it's going to be okay. And I'm going to deburr everything that we've done here so far before moving on to the next step. So I got a few Noga tools here from the bag of tricks to get this job done. Now we can move on to cutting the angled ends of the fingers, and for that I'm going to use my angle blocks, and got this case here which always holds them in place. Oh, every time, Imperial Fist Shake. My setup here is to put a dowel pin through the hole and then use the angle block to set the angle and then clamp it down nice and tight, and then just mill it flat from here. And this setup will be, again, nice and repeatable, so I can easily do the 3 pieces. And what I'm doing is I'm milling down in multiple passes. Rather than try to calculate exactly how deep this needs to be, I'm just sneaking up on it, and I check the dimension as I go using a depth micrometer because I know that my final wall thickness needs to be 100 thou all the way around the pin. So I mill down until I achieve that, and then that setting on the quill DRO tells me how deep to go for the rest of the parts. And we have 2 angles on 3 parts, so we have 6 of these angles to cut. So after the first one, the other 5 go very, very fast because I've done all the math, and I just have to set up each one once again using the pin and the angle block. And I think after a little deburring, that will look pretty handsome. All right, moment of truth time. I finally have the parts to the point where they will actually fit in the steady rest, and I can check and see how my alignment ended up on the slots. Remember, I recut these way back in part 1, and I wasn't 100% sure that I'd done it right. So now we get to find out if I did. And the good news is they do line up in the middle very well. It's not perfect. You can see some very slight misalignment on one of the fingers, so one of those slots isn't exactly perfect, but it's close enough for a steady rest. Now it's brain fart time. When I designed this part, it has a slot in the end, of course, for the bearing, and you can see that I designed it with internal radii, both for strength to prevent, stress concentrations, but also because I knew I was going to want to mill this part lying down sideways. Milling slots with the part sticking up vertically in a vise doesn't work very well. It's difficult to hold that. And yet, for some reason, I forgot I had done that when it came time to cut the first of these slots, and I set it up vertically, and then it proceeded to try and mill the slot this way. And, well, you can see what happened. As soon as the depth of cut got a little aggressive, the part moved. So luckily I caught this, and then I remembered that I had thought about this previously and changed to a horizontal setup. The good news is that past Quinn is much smarter than present Quinn, but future Quinn is also smarter than present Quinn because of the extra experience. So it would appear that present Quinn is the stupidest of the three, and thus I am always as stupid as I will ever be. Let's not think too much more about that. Regardless, the milling strategy I'm using here is the same as I used for the big slot. I'm using a larger cutter to mill out the bulk of the material down the center, and then I come back in with a much smaller cutter to clean up the surface finishes and square up the corners. This time I opted to flip the part over between passes rather than necking down the end mill and using a longer reach, because this is rough milling out the center of a slot, and so this will work out just fine. The only reason you would not want to flip the part is because it does tend to cause slight misalignment of the surfaces. The part doesn't tend to end up exactly in the same place, and you can see that little bit of a step in there caused by this approach, but that's okay because we're going to be milling this out with the smaller end mill. This is just a roughing pass, so that little step doesn't matter. So I come back in here with the same necked down 1/8 inch end mill that we used before, and again I do a clockwise lap around my slot to square up the corners and clean up the surface finishes. And this seemed to be working just fine. I did a couple of passes, and you can see how it's squared up the corners nicely there, and after deburring that should look pretty sharp. However, my milling strategy neglected to account for the fact that in this dimension the part is a lot taller than in the other one, and so my necked down end mill doesn't have the reach, so I did end up having to flip the part over for the finishing pass as well, and this is almost certain to leave a little bit of a step inside my slot, but I can clean that up with a file. And as predicted, I've got a thou, maybe a thou and a half of step there between the two passes when I flip the part over. But the more interesting problem is that the bearing doesn't actually fit. And this is after doing the math to calculate exactly where the cutter needs to be for the two sides of the slot. But even after cleaning up with a file, you can see that we're actually quite a bit undersized. I suspect this is caused by deflection in the end mill because it's a very tiny end mill. We've got a lot of stick out on it, so I did a spring pass and that got us closer to dimension. But in the end, I did end up having to make it a little bit wider on the DRO than should be necessary. And that did, in fact, then get us to the 219th thou as verified by the gauge blocks, and now our bearing fits very well. Now you can see that we're going to need clearance there on those corners, so I need to round those over. And I could set up a rotary table, or I could do various other techniques for milling curves, but it was a lot quicker and easier just to use a file. And it gives it that little bit of an artisan touch. So that's the clearance that we need, and those guys are looking good. So I did all three fingers that way, and the last operation that we need to do is to drill the hole in the end for the lead screw. I'll show you the intuitive but stupid way first, and then a better way. The intuitive way is to set it up in the mill, because it's a hole to be drilled in the end of a square vertical part. Makes sense. And this is a bit tedious to set up because you have to get it square. You put an indicator on it to make sure it's vertical, and you got to use the edge finder to find the center of it, and then you can spot it and drill it. An obligatory test fit, that works well. But here's a better way to do it. I've got a couple of scraps of aluminum L channel, and I put those around the part so that I can grip on it without getting stuck in the slot or, compressing the slot. And I set it up in the forejaw on the lathe. And now I come in here with an indicator with a ball bearing end on it, and I indicate it in. And you do this by rotating it back and forth until you get the minimum reading on the indicator, and that means your side is vertical. So then you make a note of that reading, and then you flip around 180 degrees, do the same thing on the other side, and that tells you, again, you find that minimum reading, so that tells you when the side is vertical, and then you know how far off the part is in this dimension, and then you get it centered in that dimension, and then you do the same thing on the other two sides, and now you've got it dialed in. This is just a basic technique for dialing in a square part in the forejaw. And the great thing about this technique is it saves us the edge finding, it saves us having to get the part square. The setup is just much faster and much easier doing it this way because the lathe basically takes care of all of the alignment and centering issues that you have on the mill. I like to show this kind of out-of-the-box thinking on the lathe because a lot of beginners gravitate towards the mill, especially like makers and woodworkers. They all want to run out and get a Bridgeport because I think you can look at a vertical mill and you can sort of intuitively see how it works and how it might help you. The lathe is a little less clear, but it is in fact just as powerful of a machine tool. It just requires a different way of thinking. And the lathe is also more rigid and easier to set up and has many, many fewer sources of error in it. So the lathe is by far the more useful machine tool, I think, in general, and is the one you should start with, despite every beginner wanting to run out and buy a Bridgeport. And the last operation that I'm going to do is come in here with a 2-flute carbide chamfering mill, and I'm going to chamfer all 4 corners around these fingers. And this is a very quick setup because I've aligned it to get the chamfer I want on the fixed jaw of the vise, and so then I can very quickly rotate each of the fingers through the 4 corners, just putting the corner I want to chamfer against the fixed jaw. No edge finding or anything required. And this isn't just cosmetic, although it does look very nice. This is also so that when the fingers are in the slot, there isn't going to be any kind of interference in the corners. If there's any kind of grit or imperfection in those slots, it's going to be down in those corners, and that's going to interfere with these fingers moving smoothly. All right, we are ready for some assembly. This is very exciting. There's one of our finished fingers, and the bearing slides in there very nicely. Here's those pins that we made earlier, and they slide through the middle. These tolerances are all a few tenths, so things are a little tricky to get aligned, but it slides in there beautifully, and that bearing spins perfectly. So we're very happy with how this turned out. And we have all 3 of our fingers built now, and they all slide in there really nicely. The sliding action there in those slots is really great. The time spent squaring up that stock and getting the surface finishes really, really good on it was time well spent because now these fingers are going to move and feel really good, which was the main thing that we were trying to improve on this steady rest. We have a few parts to make before this thing will be done, but we're getting really close. Thank you very much for watching, and we'll see you next time.